Hey, welcome. Have you ever looked at a messy equation and just wondered if there's a hidden, elegant pattern hiding inside? Well, today, that's exactly what we're going to find. We're going to take the roots of a polynomial, alpha and beta, and figure out how to express their powers in a way that's surprisingly simple. We're going to build the whole thing from the ground up, step by step. So here's our plan for today. First, we'll set up the challenge, what we're actually trying to do. Then we'll build our foundation with a power of 2. After that, you'll see how we use that foundation to build the power of 3, and then scale it all the way up to powers 4, 5, and 6. And stick around, because it all leads to this really cool, clear takeaway at the end.
Okay, so here's the mission. The goal is to take something that looks kind of complicated, like, say, alpha to the power of 4 plus beta to the power of 4, and rewrite it using only the most basic tools we have, just the sum of the roots and the product of the roots. It's all about breaking down the complex stuff into its simplest, most fundamental parts.
First things first, let's meet our two main characters, alpha and beta. For our purposes today, you just need to know that these are the two solutions, the roots, of a quadratic equation. Pretty much everything we do from here on out is going to be built using these two. Now, to keep our final answers looking nice and clean, we're going to use a bit of shorthand. We'll use S for the sum of the roots, alpha plus beta, and P for their product, alpha times beta. But, and this is super important, we are only going to bring these in at the very, very end of each calculation. That way we get to see the real transformation happen first.
All right, let's get into it. We're starting with the power of 2. Now, this isn't just the first step, it's our foundation. The little formula we're about to create is the most important building block we're going to have. Seriously, everything else depends on getting this one right.
So our first target is, what is alpha squared plus beta squared? And you can't just figure this out directly. But we can be a little clever and get to it from an angle, using something we already know. Here's the strategy. We'll start with something familiar, the square of the sum, so alpha plus beta, squared. When you expand that out, you get alpha squared plus 2 alpha beta plus beta squared. And look at that. The two pieces we actually want are hiding right there, inside this bigger expression. So how do we get them by themselves? It's just a little bit of algebraic shuffling. We take that whole expanded expression and we just subtract that middle piece, the 2 alpha beta. That's the key move right there. And look what happens. It simplifies perfectly. We've done it. We've managed to express alpha squared plus beta squared using only the sum of the roots, which is alpha plus beta, and the product of the roots, alpha beta. This is exactly what we wanted to do. And now, finally, we can bring in our shorthand. That whole thing just becomes s squared minus 2p. See how clean that is? This right here is our foundational tool. Let's make sure we hang on to this one. We're going to need it. Okay, we've got our foundational tool locked and loaded. Now we can move on to the next level, the power of 3. You're about to see our first building block in action. It's the key to this next puzzle. Our next goal is to do the same thing for alpha cubed plus beta cubed. And again, no guesswork here. We're going to build the answer methodically. We'll start with the standard way to factor a sum of 2 cubes. Now I want you to look really closely at that second set of parentheses. See that in there, alpha squared plus beta squared? That should look very, very familiar. It's the exact thing we just figured out. And because we figured it out, we know exactly what to do. We just have to remember our foundation from the last step. We already have the perfect tool ready to be substituted right into this new problem. This is what I mean by the building block method. So let's do the substitution. We're swapping out that alpha squared plus beta squared for our new tool, which is alpha plus beta squared minus 2 alpha beta. But wait, there was already a minus alpha beta in there, right? So we combine those and we end up with minus 3 alpha beta inside the brackets.
And now for the final touch. Let's bring in our shorthand. This whole expression boils down to just s cubed minus 3sp. It's so cool. We took another complex sum and, just by building on our last step, we turned it into a simple expression of s and p.
So now that we've got the hang of this method, we can really start to fly. We're going to use the exact same building block idea to tackle even higher powers. And this is where a really powerful recursive pattern starts to show up. Okay, this is where the pattern just gets awesome. Let's look at the first one. To get alpha to the 4th plus beta to the 4th, we can actually treat it just like our original power of 2 problem. Think of it as alpha squared plus beta squared, all squared. Then, just like before, we subtract the extra middle term, which is 2 times alpha squared beta squared. See? We are literally using our answer for n equals 2 to solve for n equals 4. It's the same for n equals 5. It uses our results for 4 and 3. Each new level is built directly on the solutions we already found. It's a beautiful recursive pattern. Now, we won't go through all the algebra, but after you do all those substitutions and you simplify everything, these are the final compact forms you get. Yeah, they look a little longer, but look closely. Every single one of them, for powers 4, 5, and 6, is still just a plain old polynomial made from our 2 original tools, S and P. No new weird terms needed. So after all that building, what's the big picture? What's the main takeaway here? Well, through all of this work, we've actually uncovered a really clear and important pattern about how these kinds of expressions behave. Let's think about it with a question. We've seen that when we take the sum of powers, like alpha squared plus beta squared, we always get a nice, clean polynomial with S and P. But what do you think happens if we try to do the same thing for the difference of powers? Well, here it is, laid out side by side. On the left, you have everything we've worked on today, expressions built on the sum of powers, and they all turn into simple polynomials. But on the right, if you try to work with the difference of powers, like alpha to the n minus beta to the n, something totally different happens. You need a new ingredient. And this right here is the key insight of the whole thing. Any expression that is built on the foundation of the difference between the roots, alpha minus beta, is always going to need this extra square root term to be expressed. That term, the square root of s squared minus 4p, is like a telltale sign, a fingerprint, that you're dealing with a difference and not a sum. This clear line between sums and differences isn't just a neat trick. It's a deep structural rule in algebra. It shows that sometimes a tiny change, like a plus to a minus, can create a fundamentally different kind of mathematical object. And it really makes you wonder, if the sum of powers has this elegant pattern, what other beautiful hidden structures are just waiting to be found inside the equations we see every day? Thanks for watching.